The Seven Bridges of Königsberg is a historically notable problem in mathematics. Its negative resolution by Leonhard Euler in 1736 laid the foundations of graph theory and prefigured the idea of topology. The city of Königsberg in Prussia was set on both sides of the Pregel River, and included two large islands which were connected to each other and the mainland by 7 bridges. The problem was to devise a walk through the city that would cross each bridge once and only once, with the provisos that the islands could only be reached by the bridges, and every bridge once accessed must be crossed to its other end. The starting and ending points of the walk need not be the same. The difficulty was the development of a technique of analysis and of subsequent tests that established this assertion with mathematical rigor. Euler's analysis. First, Euler pointed out that the choice of route inside each landmass is irrelevant. The only important feature of a route is the sequence of bridges crossed. This allowed him to reformulate the problem in abstract terms, eliminating all features except the list of land masses and the bridges connecting them. In modern terms, one replaces each landmass with an abstract vertex or node, and each bridge with an abstract connection, an edge, which only serves to record which pair of vertices is connected by that bridge. The resulting mathematical structure is called a graph. Since only the connection information is relevant, the shape of pictorial representations of a graph may be distorted in any way, without changing the graph itself. Only the existence of an edge between each pair of nodes is significant. For example, it does not matter whether the edge is drawn as straight or curved, or whether one node is to the left or right of another. Next, Euler observed that, whenever one enters a vertex by a bridge, one leaves the vertex by a bridge. In other words, during any walk in the graph, the number of times one enters a non-terminal vertex equals the number of times one leaves it. Now, if every bridge has been traversed exactly once, it follows that, for each landmass, the number of bridges touching that landmass must be even. However, all 4 of the landmasses in the original problem are touched by an odd number of bridges. In modern language, Euler shows that the possibility of a walk through a graph traversing each edge exactly once depends on the degrees of the nodes. The degree of a node is the number of edges touching it. Euler's argument shows that a necessary condition for the walk of the desired form is that the graph be connected and have exactly 0 or 2 nodes of odd degree. This condition turns out also to be sufficient, a result stated by Euler and later proven by Karl Heyerholzer. Such a walk is now called an Eulerian path or Euler walk in his honor. Further, if there are nodes of odd degree, then any Eulerian path will start at one of them and end at the other. Since the graph corresponding to historical Königsberg has 4 nodes of odd degree, it cannot have an Eulerian path. An alternative form of the problem asks for a path that traverses all bridges and also has the same starting and ending point. Such a walk is called an Eulerian circuit or an Euler tour. Such a circuit exists if, and only if, the graph is connected, and there are no nodes of odd degree at all. All Eulerian circuits are also Eulerian paths, but not all Eulerian paths are Eulerian circuits. Euler's work was presented to the St. Petersburg Academy on 26 August 1735, and published his solutia problematis ad geometrum citis pertinentos in the journal Commentarii Academiae Scientiarum Petropolitani in 1741. It is available in English in the World of Mathematics. Significance in the history of mathematics. In the history of mathematics, Euler's solution of the Königsberg bridge problem is considered to be the first theorem of graph theory and the first true proof in the theory of networks, a subject now generally regarded as a branch of combinatorics. Combinatorial problems of other types had been considered since antiquity. In addition, Euler's recognition that the key information was the number of bridges and the list of their endpoints presaged the development of topology. The difference between the actual layout and the graph schematic is a good example of the idea that topology is not concerned with the rigid shape of objects. Variations The classic statement of the problem, given above, uses unidentified nodes, that is, they are all alike except for the way in which they are connected. There is a variation in which the nodes are identified. Each node is given a unique name or color. The northern bank of the river is occupied by the Schloss, or castle, of the Blue Prince, the southern by that of the Red Prince. The east bank is home to the Bishop's Kirche, or church, and on the small island in the center is a Gasthaus, or inn. It is understood that the problems to follow should be taken in order, and begin with a statement of the original problem. It being customary among the townsmen, after some hours in the Gasthaus, to attempt to walk the bridges. Many have returned for more refreshment, claiming success. However, none have been able to repeat the feat by the light of day. Bridge 8. The Blue Prince, having analyzed the town's bridge system by means of graph theory, concludes that the bridges cannot be walked. He contrives a stealthy plan to build an 8th bridge so that he can begin in the evening at his Schloss, walk the bridges, and end at the Gasthaus to brag of his victory. Of course, he wants the Red Prince to be unable to duplicate the feat from the Red Castle. Where does the Blue Prince build the 8th bridge? Bridge 9. The Red Prince, infuriated by his brother's Gordian solution to the problem, wants to build a 9th bridge, enabling him to begin at his Schloss, walk the bridges, and end at the Gasthaus to rub dirt in his brother's face. As an extra bit of revenge, his brother should then no longer be able to walk the bridges starting at his Schloss and ending at the Gasthaus as before. Where does the Red Prince build the 9th bridge? Bridge 10. The bishop has watched this furious bridge building with dismay. It upsets the town's Weltanschauung and worse, contributes to excessive drunkenness. He wants to build a 10th bridge that allows all the inhabitants to walk the bridges and return to their own beds. Where does the bishop build the 10th bridge? Solutions reduce the city, as before, to a graph. Color each node. As in the classic problem, no Euler walk is possible. Coloring does not affect this. All 4 nodes have an odd number of edges. Bridge 8. Euler walks are possible if exactly 0 or 2 nodes have an odd number of edges. If we have 2 nodes with an odd number of edges, the walk must begin at one such node and end at the other. Since there are only 4 nodes in the puzzle, the solution is simple. The walk desired must begin at the blue node and end at the orange node. Thus, a new edge is drawn between the other 2 nodes. Since they each formerly had an odd number of edges, they must now have an even number of edges, fulfilling all conditions. This is a change in parity from an odd to even degree. Bridge 9. The 9th bridge is easy once the 8th is solved. The desire is to enable the red castle and forbid the blue castle as a starting point. The orange node remains the end of the walk and the white node is unaffected. To change the parity of both red and blue nodes, draw a new edge between them. Bridge 10. The 10th bridge takes us in a slightly different direction. The bishop wishes every citizen to return to his starting point. This is an Euler circuit and requires that all nodes be of even degree. After the solution of the 9th bridge, the red and the orange nodes have odd degree, so their parity must be changed by adding a new edge between them. Present state of the bridges. 2 of the 7 original bridges did not survive the bombing of Königsberg in World War II. 2 others were later demolished and replaced by a modern highway. The 3 other bridges remain, although only 2 of them are from Euler's time. Thus, as of 2000 update, there are 5 bridges in Kaliningrad. In terms of graph theory, 2 of the nodes now have degree 2, and the other 2 have degree 3. Therefore, an Eulerian path is now possible, but it must begin on one island and end on the other. Canterbury University in Christchurch, New Zealand, has incorporated a model of the bridges into a grass area between the old Physical Sciences Library and the Erskine Building, housing the departments of mathematics, statistics and computer science. The rivers are replaced with short bushes and the central island sports a stone toro. Rochester Institute of Technology has incorporated the puzzle into the pavement in front of the Jean Poliseni Center, an ice hockey arena that opened in 2014.